This is an enlargement of the excess air curve, the oxygen curve, and you can see there are actually two curves here. One is a dry sample, which is the typical of the portable flue gas analyzers that most people use to set up furnaces. The sample has actually had all the water extracted from it before it goes to the analyzer. There's a number of reasons for that. One is to protect the analyzer from damage. Then in the lower curve, you have a saturated sample, and this would be the curve that you would use if you have a so-called in situ oxygen analyzer, where the analyzer is stuck right in the stack and samples flue gases as they go by and provides you with a direct readout. Now, excess air can come as a result of setting a burner, and in some cases, by the way, I mean, we need it. We have to have it. We have to have quite a bit of it. You have to know the process. But a lot of times, some of the excess air that comes in is not due to a burner setting. It's air infiltration. This is especially true when we have furnaces that are fairly tall, because you get a stack effect or a chimney effect. This is what the boiler people call draft, where you can create a negative pressure inside a furnace due to that draft. And if you have any leakage, for example, around a door or through observation ports or any other place, what's going to happen is that negative pressure will draw in cold air, draw it across the load through the furnace, and then it mixes with the combustion gases and goes out the stack once it's been heated up. And so air infiltration can do three bad things. Number one, it takes heat out of the furnace and lowers your efficiency. The second is it can give you poor temperature uniformity, because your temperature is going to be colder in the furnace at the point where the air enters. And then as it heats up, it's going to be coming closer and closer to the furnace temperature. And finally, if you have a product that is exposed to oxygen, and this creates problem, for example, heat treating steel or melting of aluminum, you are now putting in a greater amount of oxygen into that furnace than you would like, and you are going to have oxidation or drossing losses, and this means that you've got a lower metal yield. Now, the way to deal with this is using a furnace pressure control system. Quite simply, a furnace pressure control system is a damper controller. They come in various forms. This one shows a so-called mechanical or clapper damper. And the reason for this is that as you change the firing rate of your combustion system, you really need a flue or a stack which changes size in proportion to it to maintain a positive pressure. Now, with most flue construction, that's impossible to do. So we can simulate the effect of changing the flue size by putting a damper on it. And so we have a probe inserted in the furnace that reads the pressure internally. And by the way, this pressure is quite low. It might only be a tenth of an inch water column or even lower. Feeds it to a controller, which compares it to a set point. And if the pressure in the furnace deviates from the set point, the furnace pressure controller then sends a signal out to an operator that will close the damper or actuate an air jet, which acts sort of like an air curtain at the top of the damper, and closes it partway to try to maintain that set point pressure within the furnace. And so this thing is responding automatically to any changes in your firing rate. And the idea, of course, is to keep the pressure in the furnace either neutral or slightly positive in most cases. And so you don't have the cold air infiltration. One of the other things that's very frequently overlooked in most industrial processes, and this would apply whether your primary mode of heating is radiant or convection, is exposure of the load to your source of heat. Now, we've shown here schematically is perhaps a high temperature furnace for heating steel or forgings, and you can see we've got on the top we've got a very single layer of pieces on the floor. On the middle drawing we've got a denser single layer, and then on the bottom drawing we've got a bunch of pieces stacked up very densely. More dense the product loading, the lower the heating speed and the lower the uniformity, because especially with radiant equipment, the only thing you're going to heat when you first start up is the surfaces that are exposed to the walls and the burners and the flames. As those pieces heat up, they then pass the heat through themselves and then conduct it to the adjacent pieces, and eventually it works its way all the way down to the bottom center of that load. The same is true with a convection oven, where you're using air to convey the heat to the product. If you have a basket full of parts that's very densely packed, it's very difficult to get that heated air through all those little nooks and crannies in that basket. And as a result, the parts on the inside of the load are going to be very, very slow to heat. And of course, the problem here is that you can't take the load out any sooner than the slowest parts come up to temperature, which means that you have some parts that are exposed to temperature far more than they need to be, and you've got a cycle that's much slower than it needs to be. Now, obviously, if you have a very light loading, you have problems with fitting enough of it on the inside the space of the furnace. And so there is a compromise here that has to be struck. Loose loading does not give you high productivity necessarily, but it does give you good uniformity and fast heating. Dense loading gives you very poor uniformity, very slow heating. Even though you've got an awful lot of material in there, the truth is you can't get it out any faster simply because you can't get the heat to the product. So look at your loading patterns. If you take all the factors in an energy balance together and figure them on the basis of your energy consumption per unit of production, one thing that comes clear very, very quickly and time after time is that your most efficient operation point for any kind of a heating device, whether it's fuel-fired or electrically heated, is at its design capacity. The reason for this is, and again, remember, we're figuring this now not in total heat to the furnace, but heat to the product. The heat to the product is going to be the same regardless of your production rate because you take it up to a certain temperature and that's it. Your fixed losses, which are the wall, conveyor, radiation, and storage losses, decrease per unit of production because they essentially are fixed numbers, so you can amortize those losses over a greater number of pieces or a greater tonnage of parts. The variable losses will increase gradually up to design capacity, but not really dramatically if the furnace is designed properly. These are your exhaust losses we're talking about. But if you try to push a piece of equipment beyond its maximum capacity, the curve begins to turn up very, very rapidly because what we're really doing now is expecting the furnace to produce more than it was designed to do. And many times the only way to do that is to set the set point temperature higher than the furnace was expected to run at, and that way you can drive the heat into the parts faster. The problem, of course, is that if you have a fuel-fired furnace, your flue gas losses go away much, much higher. So what do we do? Well, if it's a fuel-fired furnace, the first thing you do is look at your flue gas losses, which are probably your single biggest loss, and try to recover some of that heat. And you're going to do that most commonly by putting the heat back into the process via the combustion air. Here's some general numbers giving you some idea how much energy you can save by preheating your combustion air. If we take, again, that furnace example we had before of a 2,000 degree furnace, and let's say that we preheat the combustion air to 800 degrees, which is very, very feasible using air preheaters, we're going to save 26% of the total energy into that furnace. If we can get a air preheater that will give us 1,000 degrees combustion air temperature, we're going to save 31%. And you can see the numbers here. The higher the temperature, the greater the potential for heat recovery from your exhaust.